And so the second treat of the session is brought to you by Anand Natarajan, provided he manages to set up his computer. So, is it okay? Okay, great. And so Anand is going to tell us about joint work with Aram Haro and Xiaodi Wu on limitations of semi-definite programs for separable states and entangled games.
Okay. Is this working? Okay. So, right. So, yeah, I'm going to tell you about limitations of semi-definite programs for some problems relating to quantum entanglement. So just as an overview of what this talk is about, there are a couple of optimization problems that arise in the study of quantum entanglement that seem to be difficult to solve. And sort of the best known algorithms for them are based on a technique called semi-definite programming, and in particular one method of generating these programs called the sum of squares hierarchy. So in this talk we show instances where this hierarchy does not do well, and indeed no semi-definite program can do well. And these results have no complexity assumptions behind them. So let me explain what that means in more detail. So first, to introduce some terminology, we talk a lot about optimization problems. So an optimization problem is basically, to find the maximum of some function f over a feasible set S. And the problems we consider are actually a subclass called polynomial optimization, where f is itself a polynomial function in many variables, and S is some set defined by polynomial constraints. So it could have equality constraints, or it could have inequality constraints. So there are a few easy cases of this problem that we can solve. For instance, if f is a linear function and there's an efficient algorithm for testing membership in the set S, then we can solve this problem. But otherwise, in general, we have to look for approximations. So one popular technique for approximating these things is called the method of convex relaxations. So the idea is you have some set S that's very complicated, that you can't really directly optimize over. Look for a simple set S prime that contains S, and then do the maximization over S prime. So if S prime contains S, then the maximum you get will be an upper bound on the true value. And if you picked S prime well, then this should be pretty close to the actual answer. So when I said that S prime should be simple, there's some ways we can quantify that. So often one looks for S primes that can be generated in the following way. So take some cone, either the cone of positive semi-definite matrices or some polyhedral cone, and then intersect it with a hyperplane and project down to some lower dimension. So for instance, if you take the cone of positive semi-definite matrices, the set S prime you get will be characterized by a semi-definite program. Or if you take some other cone, you can get linear programming or other types of convex programming. And so there's actually a systematic technique for generating these S primes for any polynomial optimization problem. And this is called sum of squares. And basically it has a parameter called k, which is the degree. And as you adjust this parameter, this gives you S primes that come from cones in higher and higher dimensions. So basically, if I run sum of squares at degree k, I obtain an S prime that's described by O of n to the k variables. So this space here has dimension n to the k. Okay, so now let's move to the specific problems that we consider here. So there are two of them. The first one is this problem called best separable state. And so here's the problem. So I can define the set of separable mixed quantum states to be basically the convex hull of all the states I can get as tensor products of two mixed quantum states rho and sigma. So the idea is this is supposed to formalize the set of states that is not entangled. So any mixed quantum state that I cannot write as a convex combination of terms like this, I say is entangled. And then the problem best separable state is given a measurement operator, this m here, find the state rho in the set of separable states that maximizes its trace with M. And we want to find this maximum up to some additive error epsilon. So this problem has a number of applications. One application is the problem of entanglement detection, or which is basically if I'm given a mixed quantum state, can I determine whether it's entangled or not? And that's essentially testing for membership in this set of separable states. And due to some results in convex optimization, that's known to be equivalent to calculating this maximum. There are other applications. So there's, in complexity theory, there's a class of quantum proof systems called QMA2, where involving a verifier Arthur and two provers called Merlins who are forced to be unentangled. And so this best separable state problem tells you something about the power of this class. And there are other applications like calculating the minimum output Renyi entropy of some quantum channels, or calculating the 2 to 4 norm of a matrix, or indeed their connections to the small set expansion problem, which you may have heard of is important in classical complexity theory. So that's this best separable state problem. OK, so and I should say that I didn't show this on the previous slide, but this is indeed a polynomial optimization problem. So you can write this as in terms of constraints that are degree 2 polynomials and an objective that's a degree 4 polynomial. So how do we generate relaxations for this problem? Well, one idea that's been used a lot is this idea of monogamy of entanglement. And the way it's used to generate a relaxation is this. So if you recall, monogamy of entanglement is this principle that if I have two systems that are highly entangled with each other, for instance, A and B1 in this upper picture, then none of them can be very entangled with anything else. So A cannot be highly entangled with either B2 or B3 because it's entangled with B1. And so then if I took this joint state on systems A, B1, B2, and B3 and symmetrized it under exchange of the Bs, then I would have to sort of dilute the entanglement, right? Because since A could not have been highly entangled with all of these, then after symmetrization, it ends up being just weakly entangled with any one of the Bs. So then if I take the reduced state of the system, I get something that is not highly entangled. That's the idea at any rate. And so based on this, you can define a relaxation for separable states called the set of K extendable states. So this is essentially all the states that I can obtain through this process by taking a state on a larger system that has K copies of one of the subsystems that's symmetric under exchange. So the set of K extendable states is a convex set that's characterized by a semidefinite program of size d to the k if I'm working with states of dimension d. And so that's an extension, a relaxation for the set SEP. And then it turns out that this K extendable condition, together with another condition called PPT, or positive partial transpose, is equivalent to the sum of squares hierarchy at degree k. And that's something that was shown by these guys, Doherty, Perillo, and Spedalieri in 2003. So there's been a fair amount of work on trying to understand how well these relaxations work for the set SEP. So in terms of unconditional results, like for instance, just directly proving that some level of this relaxation does not characterize the set SEP well, we don't actually have any super constant lower bounds for the most general version of these relaxations. So that's essentially the ones you get out of sum of squares. So they have K extendable plus the PPT constraint and some, they have what's called full symmetry. There are, I should say, unconditional results for versions of these relaxations that don't have full symmetry, but I won't go into them here. There are also some results that are conditional on computational complexity assumptions. In particular, this assumption called the exponential time hypothesis, which says that to solve the problem 3-sat on n variables, you need time that's exponential in n. So conditional on these, you can get a number of results for this best separable state problem, both for the bipartite problem, which I described, and also a generalization to multiple parties, and for various levels of approximation. So essentially, this C and S here is if I wanted to describe the best separable state problem as a decision problem, it's distinguishing whether the maximum is above C or below S. And this K is sort of the minimum level of this hierarchy of relaxations that I need to go to in order to achieve this accuracy. So I don't want you to look at all of the rows here, but just maybe one to focus on is this last one, where for the bipartite separability problem, to distinguish between the maximum being equal to 1 or less than or equal to 0.01, I need log in the dimension levels conditional on this exponential time hypothesis. OK, so now what is our result? Well, basically, we show a comparable lower bound on these SOS relaxations, but removing the assumption of the exponential time hypothesis. So we show directly that to approximate the sets of separable states of dimension d up to any constant error epsilon, the sum of squares hierarchy requires degree that goes as log in the dimension. So this tilde here is hiding factors that are log-log or polylog-log. And as a corollary of this, really almost restating the theorem, we can say that we find states at every dimension d that satisfy all the criteria that are generated by the degree log d sum of squares relaxation. But these states are very far from any separable state. Indeed, they have trace distance, you could say, 0.99 from the set of separable states. So these are really very entangled states that are not detected by the sum of squares criterion. So that's our first result. Now our second result goes beyond sum of squares to, in fact, any semi-definite programming relaxation of the set of separable states, subject to some technical restrictions, which I won't go into here. But so our second result says that for any SDP relaxation of the set of separable states with error inverse polynomial in the dimension, this relaxation has to have size that goes as d to the log d. So note here that the error has gotten weaker. So now I'm saying that this relaxation must approximate SEP much better than in theorem 1. But this result is qualitatively stronger because I'm talking about any semi-definite program relaxation and not just this particular class of them. So those are results for the separable state problem. And one nice consequence of these is that we can say something about a class of maps called approximate disentanglers, which have been studied for a while. And so in particular, we have this corollary, which comes from theorem 2, which is that any map that is an epsilon approximate disentangler needs to have sort of an input dimension that is super polynomial in the output dimension. So just to explain what a disentangler is, it's illustrated in this picture here. A disentangler is a linear map phi that goes from states of some input dimension, here capital N, and whose image is very close to the set of separable states for some output dimension little n. So this is saying that any such disentangler that achieves a constant epsilon needs to have an input dimension that's super polynomial in the output dimension. So I believe this was conjectured by Watrous in the context of showing upper bounds on the class QMA2. And his conjecture is that you would actually need exponential in little n to be the input dimension. But as far as I know, the only version of this conjecture that was proven was one by Aaronson et al., who showed that in the 0 error case, so when epsilon is equal to 0, there is no disentangling map for any finite input and output dimension. But in the approximate case, as far as I know, this is the first version of this conjecture that has been proved. And this is a nice consequence of knowing something about general SDP relaxations of the set of separable states. OK, so now I'll talk about the second problem that we consider. And you just heard about this in detail in the previous talk, but it's the problem of non-local games. So given a non-local game with, say, 2 players, Alice and Bob, and a verifier that sends them questions and receives answers, we want to compute the maximum winning probability of Alice and Bob in this game, which I denote omega, and want to compute that up to some error epsilon. So to talk about the complexity of this problem, it's important to define the input size. And so we call that essentially the size of the alphabet from which these questions and answers are drawn. So that's what we call n for this problem. And there are several applications. This is connected to Bell inequalities, also to the complexity class MIP star of multi-prover interactive proofs with shared entanglement. And there's also connections to device-independent quantum cryptography. So why is this problem, why does it fit in this convex framework that I was talking about? Well, one way to restate it is as follows. I say that a quantum correlation is a conditional probability distribution of answers conditioned on questions that can possibly arise for some shared entangled state and measurements applied by Alice and Bob. So the set of all possible quantum correlations is a convex set. I denote it by Q. And then this game value omega is a maximization over all correlations in Q of the expected probability of winning. And so just as in the case of separable states, you can define convex relaxations based on sum of squares. In fact, it turns out you need to use a special variant of sum of squares called non-commutative sum of squares, which was introduced by these authors. But overall, it's quite similar. And again, one can ask, how well do these relaxations do? So unconditionally, I believe there were no examples for non-zero epsilon and with growing n. So there were examples with fixed finite n where this hierarchy doesn't work at some fixed level. But for growing n, we didn't really know much. However, see the talk by William Slofstra in this conference for discussion of the epsilon equals 0 case, where now we actually know that the problem is undecidable. So these hierarchies had better not do a good job there. So in terms of conditional results on the exponential time hypothesis, there's again several results. And so again, don't look at every row in this table, but one that to focus on is just this IKM row, which says that for a 2-player game, if I want to approximate the value up to an inverse polynomial in n, I need n levels of the sum of squares hierarchy conditional on the exponential time hypothesis. So now here are our results. So just like in the best separable state problem, we are able to match the result known conditional on the exponential time hypothesis, but removing that assumption. So we show that to approximate the game value up to error 1 over n squared, the sum of squares hierarchy requires degree omega of n. And then we also have this qualitatively stronger result that any SDP relaxation of the set of quantum correlations that has error 1 over n squared needs to have size n to the log n. So in the remaining time, let me say a little bit about how we prove these results. Essentially, the idea is quite simple, which is we start with a hardness result for the sum of squares relaxations for a particular classical problem called 3XOR. So if you haven't heard of this, this is sort of like a variant on 3SAT. It's a constraint satisfaction problem. And we take this hardness result and show that reductions from this 3XOR problem to the quantum problems we consider preserve this sum of squares hardness. That's the property that we call some SOS completeness. And then finally, we use some bounds in the area of extension complexity due to Lee-Raghavendra-Steurer to go from these SOS hardness results to rule out any small semi-definite program for these problems. And so here I have a diagram of how these reductions work. In the next few slides, I'll just follow one path here, starting from 3XOR and ending up with the best separable state problem. But there are many other paths, and indeed we have more results in our paper on multipartite entanglement and so on, following these other paths. So in case you're interested, you can look at those. So now in order to explain how this works, I need to tell you a little bit more about how the sum of squares technique works. So I said that sum of squares is a method for generating relaxations for any polynomial optimization problem. So how it works in particular is, say I'm given a problem that's maximize f of x subject to a constraint that some polynomial g of x should be non-negative. Well, one thing I can do just to state this problem in a sort of convex language is to say, instead of maximizing over points x, I'll maximize over probability distributions that are supported where g is non-negative. And then the objective that I maximize will be the expectation under this distribution of f of x. So that's just restating the problem in a different language. I haven't changed anything because I can always take the probability distribution that's concentrated on the point that achieves the maximum. And now what sum of squares does is it relaxes the requirement that I consider a probability distribution. So instead of a true distribution, I just ask for something that looks like a distribution up to some computationally simple tests. So this object is called a pseudo distribution, and it's encoded by something called a pseudo expectation, which is a linear map that takes polynomials to real numbers and is supposed to behave like an expectation value. So what are these computationally simple tests? They basically ask that the expectation of any squared polynomial should be non-negative. Certainly that's true for any real probability distribution, so it should also be true for this thing that we claim to be a probability distribution. And so we require that, and you also can require that this constraint g of x greater than or equal to 0 also hold under this pseudo expectation, and indeed it should hold when multiplied by any squared polynomial. So the way you get hierarchies of relaxations is you can adjust the degree to which these pseudo distributions need to be defined. So this E tilde is a map from degree k polynomials to the reals, and if I increase the k for which E tilde has to be defined, I get better and better approximations to the set of true distributions. So I get tighter and tighter relaxations of my original problem. So to show that degree k sum of squares does not work, I basically need to show that it believes that an impossible thing exists. So I need to show that essentially there's a pseudo distribution that's very far from any true distribution. So that's how I'd like to understand this SOS Hardness result for 3 XOR. So if we consider the problem 3 XOR, you can show that if I take a random instance of this with n variables and on the order of n clauses, then the maximum number of clauses that can be satisfied is basically half plus epsilon. So I can only satisfy half fraction of the clauses. However, in the degree k sum of squares world, where whenever k is less than, say, n over 100, it turns out that you can find a pseudo distribution under which the fraction of clauses satisfied is equal to 1. So this is kind of like this famous Escher drawing here. And so there's like this manifestly impossible situation, but if I'm, say, one of these guys walking around on the staircase and I only look at the steps in front of me and behind me, I can't really tell that it's impossible. That's what's going on here, is that the sum of squares algorithm cannot tell that all of these clauses are not simultaneously satisfiable, and so it produces this pseudo distribution. So this result was proved by Grigoriev in 2001. So now what we do is we start from that result, and then we transform it into a hardness result for the best separable state problem. And the way we do that is we follow a reduction based on a protocol for the problem 3-stat in the class QMA2. This protocol is due to Haro and Montanaro, and it's in turn based on earlier work by Aaronson et al. And if I view this protocol as a reduction between problems, basically what it does is the following. For every assignment to the variables in my 3 XOR problem, that's a string in 0, 1 to the n, it maps it to some separable state, rho sub x. And for every instance of 3 XOR, it gets mapped to a measurement. And this measurement has the property that the value of best separable state on this measurement is equal to the maximum fraction of clauses that could be satisfied on phi. So now this says that best separable state is at least as hard as solving for max sat of phi. Now if I view the same reduction in the pseudo world, what does it do to pseudo distributions? Well, if I start with a pseudo distribution over assignments, it gets mapped to some possibly entangled state, rho tilde. And then similarly, any instance gets mapped to a measurement. And now this state satisfies the property that trace of m on rho tilde is equal to the pseudo expectation of the maximum fraction of clauses that is satisfied. So now why does this show that sum of squares does not do a good job for best separable state? Well, basically, if we recall the pseudo expectation of Grigoriev from the previous slide, for that pseudo expectation E tilde, this E tilde of max sat of phi was equal to 1. So then when I push it through the reduction, I get a state rho tilde that has trace m phi rho tilde equal to 1. Now we show that this state rho tilde passes all of the tests produced by sum of squares. However, it cannot be a separable state because we know from the real world that the best separable state value of this measurement m was actually only a half. So therefore, this state rho tilde has to be far from the set of separable states in trace distance. So that's the idea behind the proof of the SOS lower bounds. We basically follow the same idea also for non-local games. And now just say a few words about the how we get lower bounds on general semi-definite programs. So essentially what we do is we use a theorem due to Lee-Raghavendra-Steurer that relates the power of any semi-definite programming relaxation to these SOS hierarchies. And here is a version of this theorem. I have scare quotes around the word theorem because this is not actually true as I stated it. But the morally correct version is that for any optimization problem, if sum of squares requires, on the order of n levels to solve that problem, then any semi-definite program that achieves the same accuracy has to have size at least n to the log n. Now there are two things that are wrong with the theorem as I stated it here. One of them is that this is not actually true for any optimization problem. It's only true for optimization problems over the Boolean hypercube, over the set 0, 1 to the n. And our problem best separable state or non-local game is they don't satisfy this condition, right? They're over some other feasible set. And then the second issue is that the objective function of the optimization problem has to have a certain property which I call self-reducibility. Essentially that instances of, on a small number of variables should be embeddable into instances with a larger number of variables. That's something that holds for constraint satisfaction problems, but it doesn't hold for the problems that we consider. So in order to apply this theorem, we have to basically find a subproblem of the best separable state problem or the games problem which satisfies these two conditions. And so what we do is we define a problem called honest best separable state, which is essentially to calculate the best separable state but only over a restricted set of separable states. And these separable states are precisely the ones that are produced by the Haro-Montanaro protocol. And then essentially because of the soundness analysis of this protocol, you can show that this problem, honest best separable state, is just as hard as the full problem best separable state. So if you obtain a hardness result for honest BSS, then it automatically becomes a hardness result for best separable state. So that deals with the first caveat. And as for the second caveat, we actually don't have a good way to deal with this. This is why our results for general SDPs are quantitatively weaker than our results for sum of squares. So if you recall, the sum of squares result for best separable state was up to constant error. But the result for general semi-definite programs was up to inverse polynomial error. And that comes from this caveat here. OK, so that's some description of how we prove our results. I'm now going to conclude with some open questions. So one, I think, long-standing open question in this field of entanglement testing is just some better intuition for the PPT constraint. So as I mentioned, a lot of earlier hardness results for these relaxations focused on the k-extendable relaxations without these extra constraints like the PPT constraint that comes out of sum of squares. So I hope that maybe the states that we construct here will give some more intuition for when PPT fails. Another interesting problem is to find tighter lower bounds. So the lower bounds we show are match the lower bounds that were known conditional on exponential time hypothesis, but they're very far from the upper bounds that we have for this problem from algorithms. There is a case where we have good upper bounds, which is a restriction to measurements of a certain class called one-way LOCC measurements. But there we don't have a lower bound that matches what we showed here. So it would be nice to find such a lower bound. And then another thing is these states that we construct are sort of very special states. They're states that are produced by applying the Haro-Montanaro protocol to this counterexample pseudo-distribution of Grigoriev. And it would be nice to understand how generic states and generic measurements behave, and whether they are also counterexamples to the sum of squares hierarchy. So now, moving sort of into the classical world, this best separable state problem, as I mentioned, has connections to some interesting classical problems. In particular, these two problems called 2-to-4 norm and small set expansion. So these have been studied quite a lot recently because of the unique games conjecture in classical computer science, which essentially says that the small set expansion problem should be NP hard. So if one could find a sum of squares or semi-definite programming hardness result for this problem, that would be perhaps evidence in favor of the unique games conjecture, and it would be quite interesting. OK, so now switching gears to games, an interesting open problem is that so all the hardness results I presented basically match the hardness results conditional on the exponential time hypothesis. So is it possible to go beyond this and get even better hardness results? And for games, we actually have some work in progress with Aram Harrow and Adam Benet-Watts that seems to suggest this is possible. And related to that, we could ask whether it's possible to show results like Grigoriev's hardness result for sum of squares directly in the setting of non-local games. And this motivates considering random instances of 3-player XOR games. And then finally, I mentioned that due to some technical features of this Lee-Raghavendra-Steurer theorem, we had quantitative losses when we applied it to the best separable state problem. It would be nice to find a version of this theorem that is more adapted for our quantum applications. Maybe it will give us stronger results. So that concludes my presentation, and thanks for listening.
We have time for questions. OK, I'll get us started. So can you put the conclusion? So on the conclusion slide, when you mentioned SOS Hardness results for games, this is for entangled games?
Yeah.
And so for entangled games, all your hardness results, none of them applies to constant approximation, do they?
That's right, yeah.
What's the reason for that?
So the reason for that is essentially we so I think the reason for this, I'm trying to remember what.
So in particular, I was wondering if it's related to the fact that we only have ETH hardness results for 2-player games. So for 2-player games, they only hold up to inverse polynomial approximation. For a larger number of players, there's constants. Does that play a role in the limitation of or not at all?
I think the reason was actually for 3-player games. So the reason is basically this step where we have to show that the SOS hardness result for 3 XOR is preserved under the reduction from 3 XOR to the game. And so this is easy to do for this IKM game, essentially because the questions in the game are all like low-degree polynomials in the original variables of the 3 XOR instance. But this is not so easy to do for the other games, like for instance the 3-player games that have constant factor hardness, because the questions there they seem to be very high degree polynomials in the original variables of the 3 XOR instance. So that's why we weren't able to achieve hardness results.
Thanks. Other questions? Okay, if there's no more questions, let's thank Anand again.